Hello, today we're going to work on classifying subsets of real numbers. In order to help, I'm going to take care of a few definitions here. First one, what is a set? A set is a well-defined collection of objects. In my picture here, the geometric shapes are the collection of objects. We'll be working with numbers here in a few minutes. An element is a single object in a set. The triangle is an example of one of the geometric shapes in my set. We will be looking at individual numbers here in a little bit. And a subset is a group of elements from another set. For my example, I've picked the round objects out of the geometric shapes. Now, we're doing subsets of real numbers. One person describes real numbers as all the numbers that can be plotted or approximated on a number line. Real numbers can be broken up into two major subsets: the rational numbers and the irrational numbers. As you will note, the rational numbers have a number of subsets inside of it. We are going to start with the smallest subset. The smallest subset of real numbers are the natural numbers. Natural numbers are also referred to as counting numbers, basically because we start with 1, then we do 2, 3, 4, 5, and continue on forever to the right. These would be the single points plotted on a number line, starting at 1 and extending to the right forever. In trying to figure out whether something is a natural number or not, I think of it as walking on a beach and counting the number of stones that one might encounter in a pile on the beach. So you might count here, come up with 6 stones. That would be a natural number, or it may turn out that you only see 1 stone, but that also is a natural number. As we expand, the next bigger subset are the whole numbers. Notice the natural numbers are inside the whole number, so any natural number is a whole number. As a matter of fact, whole numbers include all the natural numbers and zeros, so the subset of whole numbers is barely any bigger than the natural numbers. The only extra number we are including is 0. So we're going to start at 0, 1, 2, 3, 4, 5, continue on forever to the right. On the number line, once again, you'll notice we have all of the natural numbers, and we're going to include 0 as well. For the natural numbers, I suggest counting piles of stones on the beach. For whole numbers, I say count the number of objects in a box. Turns out you may have several objects in the box, or the box might be empty, so 0 is also included. The next biggest subset of real numbers are the integers. Notice the whole numbers are inside the integers, with the natural numbers inside the whole numbers. So the integers are all the counting numbers, 0, and their negatives. So note we will go on forever to the right, as we did before, but now we are also going to go on forever to the left. So we have all of our natural numbers, we got 0, and now we're going to include all of the negatives as well. So we're going to extend on forever to the left and forever to the right. Finally, the big subset here for real numbers are rational numbers. Rational numbers have been described as any number that can be written as a fraction. They use a divided by b, where b cannot be 0. Since dividing by 0 would be a problem, we do not want to divide by 0. Real easy examples would be like 2/3, 5/8. Something like 2 1/4 you may not think of as a divided by b, except if we turn it into an improper fraction, such as 9/4, you would see that it is indeed a rational number. Some of the other ones we've worked on. 6, which is a natural number, could look like a fraction by making it 6/1. Same thing for number 2, -2, which is a integer. We can make that look like a fraction by putting it over 1. We also have decimals we can work on. As long as the decimal ends, we can rewrite it as a fraction. 0.77 could be written as 77/100. So hence, decimals that end can be a rational number. 2.1 could be rewritten as 21/10. It too would be a rational number. Decimals that repeat can also be written as fractions. 0.3 repeating is the decimal approximation or representation for 1/3. 0.1 repeating is the same as 1/9. So repeating decimals are also rational numbers. Now I'd like to take a second while we're at it and talk about some other things. I always recommend simplifying any number as best as possible. So something like -20/4, if we simplify it, we would get -5. So not only is this one going to be a rational number, but -5 is an integer. So this would be an integer, a rational number, and a real number. Square root of 49, if we simplify that, we would get 7. 7 is a natural number, and therefore it would be a whole number, an integer, a rational number, and a real number. Now, we have not discussed rational numbers yet. If you think about rational numbers, they're numbers that can be written as a fraction. Irrational numbers are going to be numbers that cannot be written as a fraction. We're going to be looking for decimals that do not terminate, meaning do not stop, or do not repeat. Some typical examples are square roots, where you do not know the exact value of the square root. The square root of 5, the square root of 13, the square root of 14. You can come up with decimal approximations, but you do not know the exact value of those. Some other common examples are things like pi, whereas you've been told to use 22/7 or 3.14 for the value of pi when you're doing calculations. Note these are just approximations. Pi does not repeat, does not terminate as far as the number itself goes. Another common example is e, what is known as the natural number. This number is used a lot in population growth and decay and in economics. It is approximated approximately at 2.71828, but it too goes on forever. It is an irrational number. As we go through the next couple slides, you may want to pause and try these examples out yourself. That's up to you. First, we're going to start with -3. I recommend the inside to outside approach. If you can find the smallest group it belongs to, then it will also belong to each subset that is bigger than it. -3 is an integer, so therefore it's also a rational number and a real number. The square root of 7. Since we do not know exactly what the square root of 7 is, that would make it an irrational number and a real number. (12/2). Like I stated before, best bet is to take a second and simplify it. So 12/2 could simplify to be 6. Small subset 6 belongs to are the natural numbers. So therefore it's both a natural number, a whole number, integer, rational number, and a real number. And finally a tricky one, the square root of 0.25. Either using a calculator or your brain, you might realize that the square root of 0.25 is 0.5. 0.5 can be written as a fraction at 1/2. So therefore it is a rational number and a real number. Now, part of the reason that we include real numbers every time we do this is because, while real numbers are the major set that we're working with here, real numbers are not the biggest classification of numbers. That would be complex numbers. And real numbers are basically just a subset of those complex numbers. But you'll be working on those again later in another math class. I hope this has been helpful, and I wish you well. Thank you.